Good evening all, welcome back to another C64 video with some more coding. Some more basic coding I hope, and all the other cool stuff. Now I am sorry that I have been taking a while between these things, and it has, I kind of took a hiatus, but there is a very good reason. One is not because of this horse head. This horse head came with this. This is the steam horse. But the main reason why I haven't is because of this. I have wanted this for very long. This is the C64 Bible. This has so much in it, and look how thick that thing is. Huge. There's so much in this stuff, and I wanted to get something like this to work through rather than the other books. The other books didn't have much beyond what we already did, and there was a couple of things in there, but I figured we want something a bit more advanced. Now this is not for the beginners like the previous ones I've done, so this does have some basic things, but it's all written in a way that, you know what you're talking about, sort of thing. Alright? So, before I go any further, I have to give a big shout out to my good friend Mike Teehan, who sent me this horse head. He brought this for me. Brought it and sent it over because this was on Amazon, but you can't ship Amazon to Australia anymore. And he was incredibly kind to get this to me. And yeah, thanks man. So anyone watching this, give him a good thank you in the comments, and yeah, thanks Empty, you're a legend. Now, let's get this thing off my head before we do anything. Now this thing does have a history. It's from all the way from New Jersey, so yeah, a New Jersey horse. Oh, okay. There's that. So I think I'm all set up over here. Where's my mouse cursor? You can only see through these holes. I can't find my mouse cursor. Over here somewhere? I can't find my mouse cursor. There it is. I see that. Before I take this thing off. Yes, that is working. Oh, very good. Okay, let's. Hold on. God, am I still? Hang on. Let it go. What am I doing? I can't find my mouse cursor. Oh, stuff it. I'll take this thing off my head. There we go. I'll have to get rid of that there, yes. Yes, add these, the existing one, and the existing one, that one. Oh yeah, there I am. Let's bring that back down a bit. Alright. Whew. Ooh, yes. There we are. Am I coming in a little bit crooked? I think I might be. Stuff it. Don't need to have me completely flat, do you? No. As you can tell, I am very excited about this. I have been reading little bits into this. I have a hard time of actually where to start with this thing. There's so many cool things in this. It is simply amazing. I just noticed something. Hey Jill. Jill, here's an example for you. Oh, hang on. I'll bring on the full screen. There we go. There you go, Jill. So, yeah. There's so much stuff here, like the logarithmic stuff, mid, $sign, what does that do? Mid $sign is a string function. This function returns a substring, which is taken from within a larger string. The starting position of the substring is defined by the numeric -1 argument and the length of the substring by the numeric to argument. Both numeric arguments can have values ranging from 0 to 255. So what it does, right off the bat, completely floored me. And for those who want to know, there's the writing info. Whoop. This is an authentic one from way back when, 1983. Whoop. Can it read it? There we go. Copyright 1982, but this one is from 1983. Commodore Business Machines. So what is it? What is included? Also, Jesus Christ, the bloody table of contents is huge in itself. What's included? Okay. Our complete basic dictionary includes Commodore Basic Language commands, statements, and functions listed in alphabetical order. We've created a quick list that contains all the words and their abbreviations. This is followed by a section containing more detailed definition of each word along with basic programs to illustrate how they work. If you need an introduction to using machine language with basic programs, our layman's overview will get you started. A powerful feature of all Commodore computers is called kernel, which is spelt Kernal. It helps ensure programs you write today can be used on your Commodore computer of tomorrow. The input-output section gives you the opportunity to use your computer to the limit. It describes how to hook up and use everything from light pens and joysticks to disk drives, printers, and telecommunication devices called modems. You can explore the world of sprites, programmable characters, and high-resolution graphics for the most detailed and advanced animated pictures of the microcomputer industry. You can also enter the world of music synthesis to create your own songs and sound effects with the best built-in synthesizer available in any personal computer. If you're an experienced programmer, the soft load language situation gives you information about. If you're an experienced programmer, the soft load language section gives you information about the C64's ability to run CP/M and high-level languages. This is in addition to BASIC. Think of your C64 Programmer's Reference Guide as a useful tool to help you, and you will enjoy the hours of programming ahead of you. CP/M is a registered trademark of Digital Research Inc. Then it goes through, just tells you how to use it, syntax and whatnot. So I'm not really sure where to start. Well, we've got the C64 applications guide. Here's something. If you want to, what do we got over here? Hold on. Examples of actual statements. When you actually apply syntax to a practical situation, they're in 10%. Programming examples in the book are shown with blanks separating words and operators for the sake of readability. Normally, though BASIC doesn't require blanks between your words, unless leaving them out will give you an ambiguous or incorrect syntax. Shown below are some examples and descriptions of symbols used in the various statement parameters in the following chapters. The list is not meant to show every possibility, but to give you a better understanding how syntax examples are presented. There's just some examples stuff there. What that means, not really sure. But the software they have in this list is hilarious. Action-packed games. Advertising and merchandising. Hook your C64 up to a TV, put it in a store window with a flashing, animated, and musical message, and you've got a great point-of-purchase store display. Yeah, no one did that. Animation. Commodore Sprite graphics allow you to create real cartoons with 8 different levels so that shapes can move in front and behind each other. Oh, this is just hilarious. Babysitting. Oh. Hope that should be alright. I hope. Yeah, it's just the screensaver. The lock screen came on. Yeah. Okay. Here's one. Here's a good one. Babysitting. I shit you not. See? There, see? It gives you an example of babysitting. The C64 home babysitter cartridge can keep your youngest child occupied for hours and teach alphabet keyboard recognition at the same time. It also teaches special learning concepts and relationships. Okay. Basic programming, your Commodore 64 user's guide, and teach yourself programming series of books and tapes offer an excellent starting point. Business spreadsheet. The Commodore 64 offers the easy series of business aids including the most powerful word processor and largest spreadsheet available for any personal computer. What? Enter the fascinating world of computer networking if you hook your VIC modem to your C64 to communicate with other computer owners around the world. Okay. Not only that, you can join the Commodore Information Network, or CompuServe. You can get the latest news and updates on all Commodore products, financial information, shop at home services. You can even play games with friends you make through the information systems you join. Composing songs, yes. CPM. Dexterity training. Education, foreign language, graphics and art, yeah. Instrument control. Your Commodore 64 has a serial port, RS-232 port, and a user port for use with a variety of special industrial applications. An IEEE 488 cartridge is also available as an optional extra. Journals and creative writing. Light pen control, yes. Machine code programming, indeed we can. Payroll and forms printing. And last example that all computer systems used at the time. Recipes. Keep your recipes on your computer. Alright, let's see if we can find some coding in here. Oh, hang on, got some more. Simulations, sports data. The Source and CompuServe both offer sports information which you can get using your Commodore 64 and a VIC modem. And stock quotes. Goes through all the magazines at the time. The thing. Okay, basic programming rules. This talks about introduction. This chapter talks about basic stores and manipulates data. The topics include a brief mention of operating system components and functions, as well as the character set used in the Commodore 64. The formation of constants and variables, what types of variables they are, and how constants and variables are stored in memory. The rules of arithmetic calculation, relationship tests, string handling, and logical operations, blah blah blah. Also included are the rules for forming expressions and data conversions necessary when you're using BASIC with mixed data types. So, okay, screen, display codes, basic character set, the operating system. Yes, the C64 has an operating system. So, all this blue stuff here, this is the actual operating system of the C64. It is called kernel. Is there something wrong with my character set? Looks like there is. Anyway. The operating system is contained in read-only memory, ROM, chips, and is a combination of three separate but interrelated program modules. The basic interpreter, the kernel, the screen editor. Yeah, we all know what the basic interpreter is. The kernel handles most of the interrupt level processing in the system. For details on interrupt level processing, see Chapter 5. The kernel also does the actual input and output of data. And the screen editor controls the output to the video screen and the editing of basic programs text. In addition, the screen editor intercepts keyboard input, blah, 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 blah. Okay, so goes on integer. So integer goes on talking about integer, floating point. Oh, there, hang on. Full screen of my lovely mug.
So goes on about what integer, floating point, and string variables are. How do you use them? We all know this. And arrays, basically tables. Expressions and operators, arithmetic expressions. Relational operations, so like less than, up there. Logical operators, and not and x not. And or and not and XOR. Hierarchy of operations, yes. And expressions. Okay. String expressions, no. This is the input. We learned this already. Excuse me. I already know that one. Oh. Let's get some fun stuff. Let's see what we got. Using the get statement. What is the get statement? Most simple programs use input statement to get data from a person operating a computer. When you're dealing with more complex needs like protection from typing errors, the get statement gives you more flexibility and your program more intelligence. This section shows you how to use the get statement to add some special screen editing features to your program. The Commodore 64 has a keyboard buffer that holds up to 10 characters. That means if the computer is busy doing some operation and it's not reading the keyboard, you can still type up to 10 characters, which will be used as soon as the Commodore 64 finishes what it is doing. To demonstrate this, type this program into your Commodore 64. Okay, let's try it. So, yep. New. Okay, thank you. 10. Okay. TI $, so it's a string, equals, well, it's a variable, I should say, equals 1 2 3 1 2 3 20 if TI that is less than 1 2 3 1 1 5, then 20. What's that do? Okay, so what's this do? And run. Yeah, type mismatch and I shit you not. I typed out word for word this fucking little example it gave me. This one here. And it doesn't work. Thank you very much. Okay, that's it. Nothing happened for about 15 seconds until the program started. Only did the message hello on the screen. Imagine standing there for a movie. Since the get statement will keep going even when no character is typed, it is often necessary to put get statement into a loop so that it will have to wait until someone hits a key or until a character is received through your program. Below is the recommended form for get statement. Type new to erase your previous message. Okay. Oh, I see what I did wrong. Okay, so let's try this again. 20. Oh, wrong window. Okay, there we go. Go back to this. Yeah, see what I did wrong. I'm missing a thingy there. Oh, there's a missing quote. So let's go this again. 20. If TI that is less than that 1 2 3 1 1 5, then 20. Okay. If we run this, what's it doing? Ah, there we go. So it did take a while. Okay, so it did work. It was just my stupid fingers. Okay, please recommended form to get the get statement. Type new to erase the previous message. Your previous program. So we go new. Okay, now it's cleared from memory. So if we go list, we'll see there's nothing there. If you will remember from my last videos. So we'll go 10. Get a $, if a $, equals ... then 10. Notice that there's no space between . Okay, so I'll take it then 10 is just basically saying go to the 10. Okay, so it's a little bit of shorthand. Okay. Okay, run. Okay, in program. Notice that, hang on, it didn't tell me to go run yet. Notice that there is no space between the quote marks on this line. This indicates that an empty value and sends the program back to the get statement in a continuous loop until someone hits a key on the keyboard. Once a key is hit, the program will continue with the line following line 10. Add this to your program. Okay, so we go 100. Print a that go to 10. Okay, so we're getting a little bit more advanced into the shorthand of the programs, so that's cool. Okay, now run the program. Notice that the cursor appears on the screen, but any character you type will be printed on the screen. This 2-line program can be turned into part of a screen editor program as shown below. Oh, wow, okay. So, let's go run. So, it's almost like a word editor. It's almost okay. Break in 10. Okay, cool. So, there are many things you can do with a screen editor. You can have a flashing cursor to keep certain keys like Control Home from accidentally erasing a whole screen. You might even want to be able to use your function keys to represent whole words or phrases. And speaking of function keys, the following program lines gives each function key a special purpose. Remember, this is only the beginning of a program that you can customize for your needs. Cool. So, hold on. I'll show you a little bit. Give me a little bit. Yeah. This is what I'm trying to work around my bloody mic here. Okay. So that's what we got here. That's what we're going to type. Oop. So it's going to test if there's certain characters, and I'm guessing those characters are the function keys. Okay. So. Okay, alright. So. 20. Okay, whoop. Wrong thing. I'm still recording? Yeah, I'm still recording. Very good. So, 20. Oops. My stupid keyboard. I need a new keyboard. My spacebar gets stuck. 20. If a $sign equals, it's a string in other words, character 133, whoops, 33, hang on, I've still got my other book here. Oh crap, I'm sorry. Yeah, this is the one I'm meant to be on. See, that's what I just typed there. Now we're going to have a look at for a sec. I'm going to go back to the old book for a sec, because this has or the characters. Now, I just got to find out where they are. So what one we're after is 133. Codes from 128 to 255 are reversed images of codes 0 and 125. So, okay, ASCII and char codes. Okay, what one are we after? 133. 133. 133 is indeed F1. Where's me? There it is. Char code 133 is F1. So it's looking for if someone's put in the get function to saying I've clicked F1. So change then whoops, wrong bloody window. Okay. Then poke. What's that? 53280 8 go to 10. Okay, so it's got to poke something into memory. I think that's going to change the color. Or. So, okay, so 30. If that equals, so this is going to be F2. Char 134. Then poke 53281. I know those codes. That's the color. So if you press F1, it's going to change the text color. Press F2, it's going to change the background color. I think I know what this is. It's going to change the outside color and this side color to different colors. That's what it's doing. I remember that code. I recognize that memory address. I recognize it because I did that long time ago as a kid. Remember that very well. So, okay, 40. If equals CHR $135, then a $sign equals dear sir plus CHR $13. So let's have a look. What is CHR 13? 13 is a return. So it's going to use a character return, and I am missing, not showing you the bloody screen. I'm going to leave it on here. Alright, I'll just make myself a little bit bigger. How about that? Alright. So that one's out. So 13. So it's going to give character 13. So it's going to enter. Okay. So it's going to write dear sir, then move the character to the next line. Okay. That's cool. So it's not going to go loop back up again. Oh, because it's going to print the variable. So once it's done here, it's going to print the variable, then go back to here. Right, because we don't want to print out F1 or something like that, because nothing's going to appear because there's no matching character in the character set. 50. If that equals CHR that 136 that then a $sign equals sincerely dot CHR 13. Okay, so if we go list, let's list our entire. I just realized something. Okay. All right. Let's list. Let's see what we get. See what's in memory. Okay, so that's the entire program in memory. Even though I did all the lines out of order, doesn't matter. That's what it is in memory. It goes line by line by line. Use line numbers up here to get what you need to do. So now if we run this, okay, so we go A, B, C, D, E, F1. Changes the border color. F2. Doesn't do anything. Oh, hang on. No. Doesn't do anything. F3. Hang on, let's go down like that. F3 does a... Okay, something's gone a bit wonky. I think my character set's a bit off. F2 does nothing. F3 makes it all pink. F4, what does F4 do? Nothing. F5 does the dear sir. F6, F7, bad subscript error in 50. Oh, I see what's happened. Okay. This one has to be that. 1, 3. Oh. So let's run it again. Okay, so F6. Nothing. F7. Sincerely. MFOXDG. Aha! Kill. That works. So what we got here? How to crunch. The CHR $ numbers in parentheses come from the the chart lists different number of each character. Hold on, I'm gonna have a look at it for a second. Oh no, it is right. Oh, that is right. My bad. Yeah, that is it. Because you look at the codes that I've put in. Sorry. So if you look at the codes I've put in there. So 133 is F1. 134 is F3. So F2 down below. There's a good reason for that. I don't have my machine with me to show you a keyboard of it. But anyway, when you look at a Commodore keyboard, you've got the function keys on the side, you've got the number on top, but you've got this F1's on top. So if you press the button, it's F1. But you got it in front of it, on the front of it, you got F2. You have to hold down Shift, then F1 button to get F2. That's what this means. Because they're in different positions, it doesn't need to do that. Okay. Now to crunch. You can pack more instructions and power into your basic programs by making each program as short as possible. Yes. This process of shortening programs is called crunching. Crunching programs lets you squeeze the maximum number of instructions into your program. It also helps reduce the size of your programs, which might not otherwise run a given size. And if you're writing a program that requires the input of data such as inventory items, numbers or text, a short program will leave more memory space free to hold data. Abbreviating keywords. A list of keyword abbreviations is given in Appendix A. This is helpful when you program because you can actually crowd more information on each line using abbreviations. Most frequently used abbreviation is the question mark, which is the basic abbreviation for the print command. However, if you list a program that has abbreviations, the Commodore 64 will automatically print out the listing with the full-length keywords. If any program line exceeds 80 characters, 2 lines on the screen, with the keywords unabbreviated, and you want the keywords. If any program line exceeds 80 characters, with the keywords unabbreviated, you cannot change it. You will have to re-enter that line with the abbreviations before saving the program. Saving a program incorporates the keywords without inflating any lines because basic keywords are tokenized by the Commodore 64. Usually abbreviations are added after a program is written and it isn't going to be listed anymore before saving. Shortening program line numbers. Most programmers start their programs at line 100 and number each line at intervals of 10. This allows extra line of instructions to be added. As the program is developed, sorry, I'm going to bring back to this so you can see something. As the program is developed, one means of crunching the program after it's completed is to change the line numbers to the lowest numbers possible. Yeah, whatever. Put in multiple instructions. Yeah, okay. Remove the RAM statements, which is remarked. Use tab instead of space. Using go subroutines. Using read and data statements. And using variables for numbers. Okay. Basic language vocabulary. Okay. Okay. So I can do shortcuts. I'm going to edit this. This is basically saying when I'm inputting things, I can go, what was it? C, Shift, L. What does that do? Nothing. So what do I do? Okay. As a convenience, Commodore 64 allows you to abbreviate most keywords. Abbreviations are entered by typing enough letters of the keyword to distinguish it from other keywords. I'll do. If the last letter or graphics entered holding down the shift key, do not save many as So, oh, yeah, okay, thank you. Moving on, okay. Okay, now we're just getting a big old dictionary of commands. First, so it's back to front. So what is that? That is ascending ASC. What's ASC? ASC return a number from 0 to 255, which corresponds to the Commodore 64 Commodore ASCII value of the first character in the string. The table of Commodore 64 Commodore ASCII values shown in Appendix C. Okay. Right. Okay. Just goes through a whole heap of commands here that really don't mean much to me at this point. Random time. Time is interesting. Let's try this little time program we got here. I'm going to do a full-on reset. I'm going to do a full-on reset of the machine here. So I'll do a soft reset. And there we are. We're back. Brick. Okay, so let's try this time function. This time $sign function. Yeah. Okay. So tangent tab. Oh. TI function reads a time interval. This type of clock is called a jiffy clock. The jiffy clock value is set as 0 initialized when you power up the machine. There's 1/60th second interval timer is turned off during tape I/O. So let's try this one. So it says here 10. Print. Oh hell. Let's do some abbreviations. That. TI divided by 60 seconds since power up. Run. So it's been about 83 seconds since power up. Okay, cool. The TI $sign timer looks and works like a real clock as long as your system is powered on. The hardware interval timer or jiffy clock is read and used to update the value of TI $sign, which will give you a time string of 6 characters and hours, minutes, and seconds. The TI $sign timer can also be assigned an arbitrary starting point, similar to the way you set your wristwatch. The value of TI $sign is not accurate after tape I/O. So let's try this little program. So we go. Yeah. Okay. 1 TI $sign equals 1 2 3 1 2 3. So it's essentially a global variable which you can read and write from. So 4 J equals 1 2 1 0 1 2 3. Next, print TI $sign. That's all looks pretty good to me, so let's run it. What's it doing? Oh, there we go. Hey. So it's been about 11 seconds it took to count, 10,000. All right. That works. Verify. That's used to verify tapes and files. Val turns the numeric value representing the data in the string argument, blah, blah, blah. The keyboard features, don't want that. Examples of the wait statement. Screen editor. What's this? I'm not going to do that one. Don't care about that one. I've got a lot of stuff. Programming graphics on the Commodore 64. What time are we up to? Yeah, we've got a time for this. So, graphics overview. Let's have a look at this, shall we? All the graphics abilities of the Commodore 64 came from the 65-67 video interface chip, also known as the VIC-2 chip. This chip gives a variety of graphics modes, including a 40-column by 25-line text display, a 320 by 200 dot high-resolution display, and sprites, small movable objects which make writing games simple. And if this weren't enough, many of the graphics modes can be mixed on the same screen. It is possible, for example, to define the top half of the screen to be in high resolution mode, while the bottom half is in text mode, and sprites will combine with anything. More on sprites later. First, the other graphics modes. The VIC-2 has the following graphics display modes. A. The character display modes. Standard character mode. ROM characters, RAM programmable characters. Multicolor character mode. ROM characters and RAM programmable characters. Extended background color mode, ROM characters and RAM programmable characters. The bitmap modes. Standard bitmap mode and multicolor bitmap mode. Sprites. Standard sprites and multicolored sprites. Okay, graphics locations. Some general information first. There are 1,000 possible locations on the Commodore 64 screen. Normally the screen starts at location 1024 or $0400 in hexadecimal notation. and goes to location 2023. Each of these locations is 8 bits wide. This means that it can hold any integer number from 0 to 255. Connected with screen memory is a group of 1000 locations called color memory or color RAM. These start at locations 55296 or D800 in hex and go up to 56295. Each of the color RAM locations is 4 bits wide, which means that it can hold an integer number from 0 to 15. Since there are 16 possible colors the Commodore 64 can use, this works out well. No, that's the reason why there's only 16. In addition, there are 256 different characters that can be displayed at any time. For normal screen display, each of the 1000 locations in screen memory contains a code number which tells the VIC-2 chip which character to display at that screen location. The various graphics modes are selected by the 47 control registers of the VIC-2 chip. Many of the graphics functions can be controlled by poking the correct value into one of the registers. The VIC-2 chip is located starting at 53248 or D000 in hex through 53294 or D02E in hex. Okay, video bank selection. The VIC-2 can access 16K of memory at a time. Since there are... Hold on. Screen's gone. A bit wonky there. Still there? Good. Me Hagrid hair. Alright, the VIC-2 can access or see 16K of memory at a time. Since there is 64K of memory in the Commodore 64, you want to be able to have the VIC-2 chip see all of it. There is a way. There are 4 possible banks or sections of 16K of memory. All that is needed is some means of controlling which 16K bank the VIC-2 chip looks at. In that way, the chip can see the entire 64K of memory. The bank select chips that allow you to access all the different sections of memory are located in the 6526 Complex Interface Adapter Chip number 2, or the CIA-2. The poke and peek basic statements or their machine language versions are used to select a bank by controlling bits 1 and 0 of port A of the CIA number 2. Locations 56576 or DD00. These 2 bits must be set to outputs by setting the bits 0 to 1 of location 56578 or DD02 to change banks. The following examples shows this. Okay, so let's try this little example. Okay, so we'll go poke. Just poke. 56578. Peak. 56578. Wait a minute, this little example doesn't... It says or 3. What does that mean? Okay, it's done something, whatever it did. Poke 56576 . peak, 5.6, 5.76, and this 2.52, or let's just do. So this value is going to change the RAM banks. Syntax error. No idea. Oh, okay. Poke 5.6.5.7.6. I missed out one stinking letter. Peak 5.6.5.7.6. Oops, 6. And 2.52. Or A. A should have the following values. Okay, so switching the RAM bank. So as it's going down, it's changing the RAM banks, I think. Oh, whatever. Okay. Oh crap. Restart. Reset. Thank you. Screen memory. Alright, how are we doing on time? Well, let's see if I can find another example to look at. Stand the character. No, let's see if we can do some graphics work. Don't want to do that. Bit mode. No. Bitmap graphics. Let's do the. I know there's one here for the bitmap graphics. Okay, there's a nice little one here. Okay, let's do this nice little program here. The actual listings in this book are a little bit different than the other one. They're in a different font. They look like they've been actually typed up of sorts on a computer or something. I don't know exactly, but they look different. Come on, focus. Yeah, you can focus. So let's do that, shall we? Okay. 50 for x equals 0 to 319. Step 0.5. A wave will fill the screen. Okay, thank you. I'm not going to do the remarks of this one. Okay. 60. Y equals int. So it's an integer of 90 plus 80 multiplied by sin or sine, essentially sine x divided by 10. Boop, boop. Okay, 70 CH equals INT. I'm skipping ahead a little bit because I want to show something before we close off. Because I don't think you want to be sitting here just listening to me reading the book all this time. Let's see some action, shall we? So, alright. 80 is RO. Int the y divided by 8. $85 ln equals y and 7. Okay, I've got to figure out what this and ors are for. It did say back there it's 16-bit operators, but I didn't take much of it, so I'll have to look into that at the next time. By equals base, which I think is a function of sorts. So let's have a look. Where is that function? No such thing. ABS and ASC there is no such thing as base. I don't know what that's for. Because base plus oh, is that meant to be something I'm missing back here? I'm missing something. Oh, I skipped a bit of a program here. So, okay. I'll finish this up here. So, base plus arrow. Now this is making a bit more sense. Data 320 plus 8 divided by CH plus LN. Okay, so what I've missed was a few pages back. There's these little programs here to put us into high-res bitmap mode. There's a couple little examples there. Sorry, I'll make it a bit bigger for you. Sorry. So there's a couple ones here. Boop, boop, and a boop. This one down the bottom here. So it's that one and this one. So there's a few more lines to add before I do anything else. This is very much more advanced than anything we've done so far. And I'm actually loving this. I love this technical stuff we're doing here. Yeah, that looks fine by me. Okay, 5 base equals 2 times a by 4096. Like that. Poke 53272. Peak. So essentially this is what we're doing. So we're putting the value in, or 8. So we're essentially how do I explain this? Hold on. Yeah, or So we've got the AND operators here. Now this is going to be complicated. So what it does is it compares two values, but it does it in a binary form. So what this OR statement does, it goes across each of these numbers up the top here, and goes, do any of them equal 1? Then the result equals 1. If both of them are 0, then it's 0. If there's the AND says if they're both 1, then it's 1. Then you've got and OR and NOT, so it essentially inverts it, and XOR, or exclusive OR. So you can have one or the other, but not both. That's what that means. Now I've lost my spot. God damn it. Graphics. There we go. So, because right now I'm doing a peaky here. So we go peak. Oh, what did I do? Wrong one. Oh, I've lost myself. Once again. Oh, there we go. Hey, I'm back. Okay. Wrong bloody window again. Okay. So what it does, it goes peak, here we go, poke. We go peak. So it essentially takes its own value, so it grabs the memory value and uses an OR against a value called 8. Value of 8 in binary, which is so 1, 2, 4, 6, 2, 4. No, it's 1, 2, 4, 8. So it's going to flip the 4th bit. That is what it's doing. It's flipping the 4th bit. Okay, 2, 7, 2, or 8. Essentially, put bitmap at. We'll put bitmap at 8192. Okay. Alright, okay, 10. So that's where base came from. So 10. Poke. 53265. Peek. So poking, we're putting stuff into memory. Peeking, we're looking at it. We're not taking it out, we're just looking at it. 53265 or 32. So we're just going to put ourselves into bitmap mode. That's what that does. Now run the program. So what we need to do, I can't. It says in the manual to run those 2 lines, but I can't because there's all the other ones I've already written. So let's go on to the next one. It's going to be a big thing. So 20 for I equals base to base. So base essentially is, what is base? Base is the VIC2 chip. Well, looks at it. Where the location of the VIC2 chip. And base to base plus 2 plus 7999. Poke. So poke 0. So essentially this clears out the clears any bitmap that's already there. So memory 30 for I equals 1024. So basically this is clearing this the bitmap of the screen, so clearing the screen essentially to 2023 poke I3. Hold on. That's changing the color of the screen. Next. Set color to cyan and black. Okay. Says now run the program, but I can't because I already typed everything in. Okay. Okay, so it says here, now run the program. As you can see, the screen clearing, then a greenish blue color cyan should cover the whole screen. What we want to do now is turn the dots on and off in high-res screen. To set a dot, turn a dot on, or unset a dot, turn a dot off, you must know where to find the correct bit in the character memory that you have to set to 1. In other words, you have to find the character you need to change, the row of the character, and which bit of the row that you have to change. You need a formula to calculate this. We will use X, Y to stand for the horizontal and vertical positions of the dot. The dot where X equals 0 and Y equals 0 is the upper left of the display. So to that video, it's up. Hold on. It's up under my head up here. So that's where the start of the screen is. Dots to the right have higher X values and the dots towards the bottom have higher Y values. Best way to use bit mapping is to arrange the bitmap display something like this. Each dot will have an X and Y coordinate. With this format, it is easy to control any dot on the screen. However, you actually have to have something like this. So what's this mean? So I actually have to have a table of sorts, by the looks of it, for each row. Programmable characters which go A bit of that body is Now we put these formulas together. The body in which character memory dot XY is located. Oh, excuse me. Calculated by byte equals base plus row times by 230 plus character times by 8 plus line. Turn on any bit in the grid of the coordinates in XY to use this line. And some calculations value. So, okay. So now I've got some stuff to work with. Okay, so next. Okay. I missed something, didn't I? Looking at the last one. No, I didn't. Okay. 100. So 100. BI equals 7 minus X and 7 110 POKE poke BY peak BY or 2 to the power of BI, whatever that is. Next, X, oops, 120. Next, X, 125. Poke 1024 Come on. 1 6 1 3 0. Go to 1 3 0. So it does an infinite loop at the end of that. Okay. All right. So let's list this. Let's do a bit of a review first. Okay. Base is that, poke, that, peek it by that, by all that. Poke, peek, that, all that. For I, base to base, that. So what is it? What was it? 7? Yeah, 7999. Okay. Poke, I, 0. Okay. Next. Okay, so looks fine to me. Let's run it. See how we go. Okay, so now it's clearing itself up a little bit. So it's clearing up, doing something, whatever it's doing. I don't know what it's doing, but it's doing something. Okay, so it's clearing up the screen. Alright. That's good. It's doing something. Alright. Getting rid of all the garbled stuff out of it. And now it's filling up the entire screen like that. And now it's drawing our sine curve. Oh, that is so cool. Haha! We did it. We did some really advanced basic here. We are manipulating the very pixels. That is cool. Wow, what a way to end this video of a new start. And I can't wait to see what we can do further on. Oh my god. This is cool. So, if you like this video, please, give the thumbs up and all that. Like, subscribe, all that stuff. If you want me to go on, please tell me. I would love to, and I will be more than happy to. Thank you so much. And once again, big thank you to my friend Mike Teehan, aka Empty. You're a fucking legend, mate. So anyway, we have a lot to go through. We have a lot of stuff. And what's this? The dancing mouse. Oh, the sprites. And we can learn sprite collisions and stuff, which is cute. And some sound and music properly, ring modulation and all that. Subroutines, indexing. Ooh. Whoa. What do we got here? Ooh. Ah. Yes, we are now getting into, over here, we got the machine language. We got assembly. Sweet. And there we go. Our sine wave is finished. So we have a lot. I can't wait to get into this. We've got the memory map. We've got all this sort of really awesome stuff to go through. And I can't wait. We've got music notes. We've got the Vic register map. We've got all this stuff. Look at this block diagram of how the whole thing actually works. You don't get that anymore. Oh my god. Wow. Look at all this shit we got. We've got the timing diagrams of all the chips. We've got so much stuff in here. We've got big pictures of the chips themselves. And best of all, I have to say this. And thank you so much, Empty, for finding one that still has this. Hold on, I need to get a bigger me for this. Where am I? Yeah. You have the whole friggin' schematic of the whole goddamn machine. How awesome is that? How many of these modern day machines give you that? None. Ah, the good old days. They give you everything you need and let you go. Alright. So once again, thank you so much for watching. Like, subscribe, and all that. Once again, thank you so much, MT. You're a legend. And I'll see you all in the next one. Bye for now. Bye-bye.